Hello YouTube, in this video we're going to be continuing my series of videos on the multiplication rules for probabilities, except for in this video we're going to be discussing specifically not independent events but dependent events. Okay, so at the beginning of this it's very important that we actually take the time to define what we mean by dependent events. And so we'll look at the technical definition up here. We say when the outcome or the occurrence of a first event that happens in a sequence of events affects the outcome or occurrence of the second event in such a way that the probability is changed, then the events are said to be dependent events. So these are like linked events. That would be something that I do the first time that affects what happens the next time. And often you see in thought experiments things like, you draw a card from a deck of cards and you don't put it back, okay? Or, let's say you need to choose a combination and, you can't repeat digits. So you have so many digits to choose from for the first spot, but not as many in the next spot, or so on and so forth. But basically we say dependent events. I give a few examples here. We say drawing a card from a deck, not replacing it, and then drawing a second card. The fact that you didn't put the first card back would affect the outcome of the second card occurring. So we say, how about selecting a ball from a bag, not replacing it? There you go. Selecting a second ball. How about being a lifeguard and getting a suntan? I mean, like, hey, the fact that you get a suntan, which happens later, is probably because we've already established your lifeguard. It has some effect on your suntan. Having high grades, getting a scholarship, parking in a no parking zone, and getting a parking ticket. Ooh, okay, so, we're starting to look at how likely something is to happen down the road, given that certain things happened already. So we talk about, a lot of the time, conditional probability, the base word here being condition, based upon a prior condition, okay? So it says, consider the following thought experiment. Determine the probability of drawing an ace from a deck of cards on the first draw, not replacing that card, and then drawing a king on the second draw. So typically, or at least according to my last video, we would have said ace on the first draw, and okay, looks like king on the second one. So according to our last video, we could actually just split this up. We say probability of an ace then on the first draw times probability of a king on the second draw, because and means times. It's just that I want to, when we evaluate it this time, consider this thought experiment. Think carefully. We say the likelihood of getting an ace now, out of 52 cards, out of 52, there are 4 aces. And we say times the probability of getting a king. Now, assume this. This king that we're drawing out here, we are drawing it out from a deck in which we did not put that first ace back. Like this first ace has already happened. Past tense, past. Okay. So we'd say instead of out of 52 cards now, we have a deck of 51, and there are 4 kings because we didn't remove any kings. But the bottom line is, this is a significant change. And as a matter of fact, I cannot sit here and tell you that the probability of getting a king in a deck of cards is 4 out of 51, because it's not. The probability of grabbing a king is 4 out of 52. So in this case, we're going to have to find a different way to write probability of king in such a way that it means that we assume that, we're probability of getting a king, but given that the first thing already happened. So we refer to this as writing it as, instead of PK, we say probability king given that ace already happened. So a few notes I'd like to make about this one. We say king, this is the second event here. We say the second event happens given that the first event already happened. Okay, and this middle bar here, we read it as given that blank already happened. Okay. So a few things to say about this. We say, the event on that last example of getting a king on the second draw, given that the ace was drawn the first time, is called a conditional probability. So this thing right here has a name. It's referred to as a conditional. We'll define it more on the next page. But conditional probability, because we're saying how likely is it that this thing happens here, this first thing happens here, given that the other thing had already happened. Okay, and so we say it's based upon prior condition that the first thing already happens. We'll call it conditional. All right, so here's the deal. Conditional probability says the conditional probability of an event B, so the second event, in relationship to an event A, is the probability that the event B occurs down the road, given that A already happened. So we say the notation for conditional probability, which is that P second event happens, given that first event already happened. Okay. This does not mean divide. Divide. Don't do it. It's not divide. Okay. So we're going to take a look at a second rule we've got here, but multiplication rule number 2 in terms of how to evaluate for P, A, and B when you have dependent events. What I'm going to tell you is this. Whether you have independent or dependent events, everybody should be using this rule right here. Write it down, because what it says is this. Essentially, if you want to find the probability of A and B, it's the probability of the first thing times the probability of the second thing, probability B, but given that A already happened. So consider two events that are completely independent. Let's go back to our coin and die example. What if we were flipping a coin and rolling a die? We say, how likely is it? I get probability of flipping a heads and getting a 4. If we use this rule right here, then it would be rewritten as probability of heads times probability of 4, but given that heads was already flipped. Now, what do we know about flipping a coin and rolling a die? Well, we know that these are independent events. So wait, this is the rule to use when they're dependent events, but can I use this when they're independent also? So we say probability of heads is 1 out of 2. Now, get this. The question for the second one we're trying to answer here is this. How likely is it that we roll a 4 on the die given that we flipped the heads before? And since the heads doesn't affect that, it's still a 1 in 6 chance. So we can just go ahead and use this rule all the time for dependent events, even for independent events. So let's take a look at these next two examples, common examples. We say, okay, so a person owns a collection of 30 CDs, of which 5 are hip-hop. It says if 2 CDs are selected at random, find the probability that both of the selected CDs are hip-hop. I want to be clear on this one. I could have made it clear when I wrote this, but I say 2 CDs are selected at random. Look at it this way. We're taking a CD out and not putting it back, and then taking another CD out. And so that's what makes these dependent events. Okay, so we're going to start by drawing our sample space. Let's construct this here. And basically what we know is this. We say, all right, hip-hop is this H here. We've got 5 of these, and then like other. And the other 25 are in the collection for a grand total of 30. So if this is our sample space here, we say, well, read the last sentence here. Last sentence, it says, find the probability that both are hip-hop. So probability hip-hop, and then in sequence, another hip-hop. So we'll call this hip-hop 1, hip-hop 2. Rewriting this with a rule, though, we say, well, then this is just probability first thing, which is hip-hop 1, times probability second thing. It's just that we're putting this fancy /H1 in here, which basically means, look, what's the probability of the first thing times probability of the second thing, given that the first thing already happened? So probability of getting a hip-hop in the first place, we say, well, this is 5 out of 25. Now, what this example is good at showing is this. We say, now what's the likelihood we get a hip-hop on the second CD, given that we took a hip-hop out? And that hip-hop coming out affected this probability. So we say, instead of having 5 hip-hops to choose from now, we only have 4 left. Instead of being out of 25, it's out of 24. So we could reduce all this as much as we possibly can. First, we say 5/25 is the same thing as 1 over 5. 4/24 is the same thing as 1 over 6. And so this produces a 1 in 30 chance, or man, it'd be 0.033 repeating. I'm not sure. About 3.33% chance, I'm guessing. So anyways, yeah, this is how you would use this rule. And again, with this rule down here, this last example, it says the worldwide insurance company found that 53% of residents had homeowners insurance with the company. And it says of those clients, 27% also had auto insurance with the company. If a resident is selected as random, find the probability the resident has both homeowners and automobile insurance in the worldwide insurance company. Honestly, do not get intimidated by this. You read the last sentence here. Tells you what it was. It says probability homeowners, we'll call that H, and auto with this. So we've already got the probability we need. Let's rewrite this. This is the probability of the first thing times probability of the second thing now, given that the first thing already happened. And so now, nice thing about it is we've already actually technically been hooked up with these probabilities. We say, the worldwide insurance company found 53% of its residents had homeowners. Well, then the probability of grabbing a homeowners is 53%. It's just that we need to write it as a decimal. And over here we say, well, then what's the probability that they have auto, given that they already had homeowners with the company? That's the second sentence here where I say, of these clients that already had homeowners, 27% also had auto. So we say this is 27% auto, given that they already had homeowners. It's just trying to pick these word problems apart. So we say, 0.53 times 0.27, 0.53 times 0.27, 0.1431. So about a 14.31% chance. So 0.1431, approximately 14.31% chance. So the last note I want to make on this video is essentially this, but it says the multiplication rule can be extended to include 3 or more events, even if they're dependent. So if we said, what's the probability I get, say, jack, and then a jack, and then a jack, you know, like jack 1, jack 2, jack 3, then it'd be probability of the first thing times probability of the second thing, given that the first thing already happened, times probability of the third thing, given that the second jack was drawn after the first jack was drawn. So just know this, if I had said like probability jack, and then a jack, and then a jack, and I do this like 5 times, and then a jack, and then a jack. You know, rewriting this isn't going to be fun, but essentially what you're going to see is this pattern, you know, where we multiply for every and here. But we're going to get this first jack is really 4 out of 52, but then not putting that back, we only have like 3 out of 51, times 2 out of 50, times only 1 left there out of 49. And since we take that 1 out, we say, well, in this last one, there are no jacks left to draw from, even though it's out of 48, you know, so I got a whole deck here. Basically because, you know, I've already taken the 4 jacks out of the deck. Well, basically, if I said, how likely is it you draw 5 jacks? It should be 0. All this goes to 0 with this 0 right here, because it's impossible to draw 5 jacks out of a deck of cards. So this is just a quick intro to dependent event probabilities with multiplication rule. In the next video, we're going to take a look at conditional probabilities and calculating them on their own.